let's look at this box here, and this is just the final example before we get into my PowerPoint. So this is a box, right? And suppose that we have an electric field that is pointing like this. Now, let's say that the side is equal to A. Now, what is the interesting point here? I know that a box has 6 sides, but in this problem, you see that the electric field is only going through 2 surfaces, the surface at the bottom and the surface at the top. So even though there is 6 surfaces, I need to only focus on 2. Because the electric field is not coming in any. So let me call this surface number 1 here and surface number 2. So I don't need to worry about surface number 4, surface number 5 on the sides, and then the surfaces at the back and the front. Are you guys with me? Mm-hmm. So I'm talking about 6 surfaces here, bottom, top, left and right, front and back, right? So because the electric field is pointing in the Z direction, I need to only focus on the bottom and the top. All right. So when I calculate the flux, the total electric field, I only need to focus on 2 surface areas. And these are the surface areas that I'm interested in. This one, this one. And I think this is really where we're going to establish a final equation here. Let's look at the area at the bottom. Remember we said that the unit vector of the area, and I'll write this again here. So this is something that you want to really keep this in mind. So the area vector must, this is by definition, must point this is the key point. This is important. The area vector must point outwards at 90 degrees respect
So does that mean the top would point up and the bottom would point down?
Exactly, that's correct. So it means that at the bottom, my unit vector for the area is like that. Again, let me put, so let's call this direction here X, let's call that direction Y, and then this is my Z. So it means that my electric field, so let's write the electric field as some magnitude, pointing in the k-hat direction. Then I'm going to write the area at the bottom is A squared, but this is pointing in the negative k-hat direction. And the area at the top is A squared, pointing in the plus k-hat direction. So in this case, what do you think is the total flux? So when I calculate the total flux, I take the electric field, I dot it with the vector of the area at the bottom, plus the electric field, dot with the area at the top. So what should that give me? 0. Does everyone agree with this? That the total flux, so in this case here, again, if you do this carefully, you get negative E A squared plus
Does it say AT? What does that mean? Oh, like,
It's the
oh,
area
top
at
and
the
bottom?
top, right, yeah. So B is for bottom. That's for bottom. And T is for top. Now, with this, I'll write down one equation here. So the electric flux is always 0. Unless and this is called the Gauss's law. The electric field through a closed surface is always 0 unless there is a charge inside the bond.
What if the electric field isn't uniform?
What if it is non-uniform?
Yeah.
That's a very, very good question. So, and I want to show one example here. That's a really good question. So let's look at this example here. So let's look at the example of a point charge. So for a point charge, we have a, then we said that, remember that for a point charge, the electric field lines this is an example of a non-uniform, right? Because the electric field is not the same, it's changing. Right? Now, let me draw a surface right here. Later on, we're going to call this, we're going to give it a name called the Gaussian. Now, let's see what is happening here. Now, this, even though I'm drawing it like that, but think about this as a sphere, right? Because, again, you can only use, so far, we only need to focus on the closed surface. So let's see what happens here. Let's look at point A and point B. You see that as the electric field is going into point A, you see that my area vector is pointing that way. And at point B, my area vector is pointing that way. So when I calculate the flux in this volume, what do I get?
0.
I get 0. I still get 0. So 0 means that electric field is going in one direction and coming out in the other direction. So the net effect is 0. Now let's see what happens, and we're going to talk about this in the next class. What if I draw a surface like this? Now, because this surface contains a charge in it, when I calculate the electric flux now, it's not going to be equal to 0. So this is what I want to talk about in the next class, and this will lead us into the Gauss's law. All right, so if you guys have the time, just maybe look at the PowerPoint. So on Friday, we'll wrap this up and then do a review for the exam next week on Monday.